So housekeeping items for today being March 19th. If you have not already, turn in homework 15 on Monday, and I'll give you 10 points for that. Start working on quiz 3. Do not wait till the last, day before. A lab report on rates of reaction. So that's a little bit overdue. So make sure you turn that in. I would ask each and every one of you to check the Canvas gradebook to make sure that you are up to speed with all the assignments. Lab report, rates of reaction, and then we have a lab today on Le Chatelier's principle. Okay, that's right after this class, all right? And everyone should come to that lab, except for one person. So for that one person, I am going to give him a toast. Do you drink beer, Robert? Are you a big beer fan? Beer.
Yeah, I like beer.
Okay, I toast this to you, all right? Old beer. I wouldn't drink it. It's got dents and stuff, so.
Okay. Well, I'll take a beer.
Anyways, I'm just teasing. Thanks for coming to the lab. He was the only one last week. And I would toast it to you, and I would also have one to toast, but are we a dry campus? I don't know.
Yeah.
We are dry. Okay, so hide that. Put it in your backpack. And I think that's it. All right, so homework, quiz, lab, and then a lab report for this Le Chatelier's principle will be due next week.
Are we going to start doing labs all on one day? Because I know you had mentioned that.
No, it's already, we only have less than a month in the semester. Oh, about a month. We have a month, so. Basically what Josh was saying, should we do labs every week? Because we have less than 12 people. We can, but I decided not to do that. So you can have a little more breathing room for your labs. If you're doing that online clutch prep, make sure you keep up to speed on that. And update your lab notebook. I'll collect that. I'll collect your lab notebook at the end of the semester. Okay, if you need to know how to maintain your lab notebook, come see me. I have several sample lab notebooks in my office. Okay.
Did you say it didn't need to be signed anymore?
If you can get them signed, that would be good. If you work in a real lab, in real world, they have you sign it. So that's why we have you do that. You sign it. This is probably the most important thing in the whole class, learning how to write a lab notebook. But unfortunately, we just kind of throw it off to the curb. But if you can get it signed, that would be good. If not, that's okay. All right. So make sure you do come to lab. If for whatever reason you cannot come to this lab, I did film a video. You can use that as your data. But we do want you to come to the lab. All right. I handed out a practice problem sheet. Wednesday after class, Josh over here, he asked the question, and it was a very good question. How do you know which way? He said, setting up the ice table is fine, but how do you know which way to go and all of this stuff? So that's a very valid, legitimate question. So I thought we would do another practice problem utilizing an ice table. All right, so remember, we're going to use an ice table for a weak acid or a weak base. In Wednesday's class, it was a weak base. Okay, this is what we did on Wednesday, but Josh came to me after class And he said, I can set this up just fine, but how do I know it goes this way? And I answered, you really have to look at the problem. Okay, read the problem and then decide which way the ice table is going to go. So, setting it up seems to be fine, but is it going this way or that way? It depends on the context of the problem. So let's do another one just like this. Okay. And this is something I handed out to each and every one of you. So this is a weak acid. And the question is, what is the pH of a 0.6 molar formic acid solution? The Ka of formic acid is 1.8 times 10 to the minus 4. All right, so just some context to this problem. We have formic acid here. Okay, so here's my bottle of formic acid. And they tell you the concentration is 0.6 big M. Okay, big M stands for moles over liter. Okay, that's a concentration. Tells you how concentrated the bottle is. So what I want to tell you guys is that this bottle of formic acid, okay, whatever, 100 mils, 200 mils, 500 milliliters, it doesn't matter how much. That formic acid in the bottle is not formic acid by itself. Right, so this is an important point. This is not formic acid by itself, because you see, this is a weak acid. So you have not only formic acid in this bottle, whose concentration is 0.6 molar. First of all, that formic acid is dissolved in water. And you not only have formic acid, but remember, what is an acid? Acid delivers protons. So you not only have formic acid in here, in this bottle, you have H3O+, which is H plus proton, plus you also have the conjugate base to this formic acid after it delivers that proton. So in this bottle of formic acid, you not only have your formic acid, if you just visualize this with me, but you also have protons, okay, their actual acid, and you also have this HCOO minus. So those chemical species are inside this bottle, as well as formic acid. And they tell you the Ka for this is 1.8 times 10 to the minus 4. So, how much of H plus and HCOO minus do you have? It depends on how big this Ka is. If this Ka was very large, remember, if you have $1 million, okay, are you moving forward in life? Okay, yeah, you're moving forward in life. Okay, this Ka is kind of small, 1.8 times 10 to the minus 4. So we don't know to what extent, we don't know to what degree this reaction is moving this way. Okay? Because this formic acid is not only 0.6 molar, but it contains some of this H plus, some of that HCOO minus. That's why we need to construct an ice table. It's a weak acid. You'll do the same thing for a weak base. So I, C, and E. So Joshua, this is for you. So we started out with 0.6 molar. Okay, we don't care about water because water never goes into our Ka. This bottle is 0.6 molar, but some of it is going to go this way, some of it is going to go this way. So initially we have 0. Okay, and we want to figure out the pH. Okay, we have to, what is the question? The question is, what is the pH? So, okay, pH is minus the log of the hydrogen ion concentration. So we need the hydrogen ion concentration. Okay. So some of this reaction is going to go here, this way, because, this is an equilibrium, weak acids, weak bases. It's not going to go, unless it's the 6 strong acids, unless it's one of our 6 strong acids, it's not going to go 100% this way. All right? It's going to settle. Settle here, here, here. It's going to settle. So where it settles, what is the final concentration of this, the final concentration of that, and what is the final concentration of formic acid after this is all said and done? So the change here, initial change, is going to be minus x. It's 1x because it's 1 mole. Okay, we don't care about water. It's going to be plus x here, plus 1x because it's 1 mole. And it's going to be plus x here, okay, because plus 1x because it's 1 mole. If there was a 2 here, it would be plus 2x. It's not. It's plus 1x because it's 1, okay, 1 mole. This equation is balanced, so 0.6 minus x at equilibrium plus x plus x. Right, so if you get a problem like this, okay, you want to set up your ice table and it's going to go in this direction, because at the end of the day you'll have this, this, and this. We want to know how much of all these species, all these chemicals, are inside this bottle. If this was a strong acid, we wouldn't worry. It would be 100% this and that. Or if it's a strong base, we wouldn't worry because it would be 100% base and conjugate. Okay, so our Ka here is products over reactants. All right, so concentration of H3O plus or H plus, I use them interchangeably, times the concentration of HCOO minus divided by the concentration of HCOOH. That is our equilibrium expression. By the way, this is called formic acid. It has that H that goes away. It can go away. It's called ionizable. Okay, and that is our acid. Its conjugate base, I'm going to call that Cb, is called formate, the formate ion. Okay, this thing is called water, H2O, and this is just hydromonium ion or proton. It's called hydromonium ion. You don't have to know the name, but that's what we call it technically, hydromonium. It's also known as proton. H3O plus and H plus are the same thing. At least the way I'm going to teach it to you. All right, back to our problem here. So Ka is given to us as 1.8 times 10 to the minus 4. Equals, at equilibrium, H3O plus is X. HCOO minus is also X. And HCOOH is 0.6 minus X. So, our goal here is to find X, right? Our goal here is to find X because X is the concentration of H plus. X is also the concentration of our conjugate base. This one is called formate ion. All right, let's do a little bit more manipulation here. This is 1.8 times 10 to the minus 4 equals x squared divided by 0.60 minus x. Okay, so now I'm going to do what's called the low ionization assumption. So in the low ionization assumption, we're going to assume X is small. This change, remember, change. Some of it is going this way. This is change. We assume X is small, such that 0.60 minus X is about 0.60. Okay. So this will make your life a little bit easier on an exam. Okay. Because we're assuming that this direction going this way is very, very small, or not really significant enough to change this value. It's going to move because in an equilibrium you have to, okay, it's not 100% going product side. Okay, it's not 100% reactant side. It's some balance, but we're saying the shift to the right is small because it's a weak acid with such a small equilibrium constant. So this is called, by the way, the low ionization assumption. The threshold is 5%. 5% cutoff. All right, so with our assumption intact, it's going to be 1.8 times 10 to the minus 4 equals x squared divided by 0.60. Okay, let's go ahead and solve for x here. So 1.8 times 10 to the minus 4 times 0.60. Okay, let's take that equals x squared. So let's take the square root of that to get x. Okay, remember x is here, which is our H plus concentration. So what is this on our calculator? 1.8 times 10 to the minus 4 times 0.60. Okay, don't forget to square root that answer. And I'm getting 0.0104. And here we actually put the units of big M. Now let me turn off the lights here. All right, so let's test our assumption. Okay, so remember, it's 5% cutoff. So test our assumption here. So the formula is you're going to take your x that we found, divided by the concentration initially of the acid, initial concentration of acid, and we multiply it by 100 to get a percentage. So let's do this assumption testing and see if it's below our 5% cutoff. So our x, we just found that, right? It's 0.0104 divided by the initial concentration of the acid. What's the initial concentration? The initial concentration they gave us is 0.6. Yeah. And let's multiply that by 100. If this is greater than 5%, then we have to use the quadratic equation, or so that would be a problem. Okay, multiplied by 100 to get a percentage, 1.7% ionization. Okay, well below our 5% cutoff. Our assumption passed. It did not fail. So assumption is passed. 1.7% ionized. Remember, 5% or greater means, this assumption fails. Here we're at only 1.7%, so our assumption passes. This is the answer. the cutoff, it has to be 5%. If it's greater than 5%, it's a significantly strong answer. It's a significantly strong base or significantly strong acid for which the assumption does not work. All right, so here is our answer. And let's plug that in here. Okay, X, which is the same thing as the H3O plus concentration. And now we'll do our pH is equal to minus the log of the hydrogen ion concentration. And that's minus the log, well, 0.0104 is X, which is H plus. So minus the log of 0.0104. pH has no units, so this is something you do not want to mess up on in your exam or whatever future science classes you do. So minus the log of 0.0104. And I'm getting a pH of 1.98. So that would be the pH of this weak acid, formic acid. And this is how you would do this problem. Okay, what is at equilibrium? Let's do a little bit more here. At equilibrium, when it's all said and done and the reaction has settled, we will have the concentration of H3O plus to be 0.0104. Big M. And we would have our concentration of HCOO minus. This is also called formate. We would have that concentration to be 0.0104 because it too is X. Okay. And then our concentration of formic acid at equilibrium is going to be 0.6 minus 0.0104, which equals 0.58, 0.590. Okay. So you guys see, let's draw our formic acid bottle again. You see, this is not, well, they tell you it's 0.6 molar, okay, but really 0.6 molar formic acid is not 0.6 molar. It's actually 0.010 molar HCOO minus, 0.0104 molar H plus, and 0.590 molar of the actual formic acid. So some of it has actually went this way. Okay, some of it has gone this way. So this is how you approach a problem like this. Okay, if it's at initially 0.6 molar, it's not really 0.6 molar. Okay, some of it has gone this way, some of it has gone that, some of it has gone this way to produce this, some of it has gone this way to produce the conjugate base. This is how you do this type of problem. Okay, it's along the same lines as the weak base that we did on Wednesday. So there'll be something like this on your quiz number 3, and there'll be something like this on the exam. So check your study guide for more information on that. Bless you. Bless you. All right, so wrapping up the final 3 pages or so of this chapter. What you see here in our notes, I'm on page 18 if you're following along. Don't forget the relationship here between Ka times Kb, and that equals to Kw. Okay, so conjugate acid, conjugate base. So remember, the Ka is this. This is something that you should write down on the exam. This is our standard Ka generic form. That has some Ka value. And this is our standard generic Kb form. Notice water's really doing the business here. This is our standard Kb form. For the weak acid, Ka, weak base, Kb, these are the equations. Look what water is doing. The fascinating aspect of water here, it's acting like a base in the Ka. Here, water is acting like an acid in the Kb. You substitute any weak base here, substitute the conjugate here for the Kb, and you get Kw when you add those 2 reactions together. When you add 2 reactions, you multiply the equilibrium constants. Okay, one more time. When you add 2 reactions, the equilibrium constants get added together. And this is Kw, right? Which is products over reactants. Any K, products over reactants. We don't care about water. Water is a liquid. So make sure you know this for the exam. Make sure you know this for the exam. Kw is at 25 degrees. I think I'll give this to you on the exam, but it will not hurt to memorize that constant. You may see it again. That's 1.00 times 10 to the minus 14. All right, so the main point of this is this relationship. Okay, so let's move on to our next topic here, and that is polyprotic acids. These are acids that deliver more than 1 proton. Okay. So we have something that's diprotic. The best example of something that's diprotic is H2SO4. Okay, this is called sulfuric acid. Right, so it delivers 2 protons. Okay, can deliver 2. The key point here is that the first proton has a higher Ka. So remember, sulfuric acid is one of our strong acids, okay? But it's the first proton that's stronger. It's the first proton that leaves better. Or it's the first proton that is more acidic. The second proton, not so much. Okay? So in other words, H2SO4 is a strong acid. It's one of our 6. But HSO4 minus, this is what happens when you deliver that proton, that's a weak acid. Okay, let's look at another polyprotic acid, and that is phosphoric acid. Okay, this is loaded in Coca-Colas, Coke cans. Phosphoric acid. Okay, phosphoric acid is not a strong acid. It's not part of our 6, but if it delivers a proton, okay, how many protons can this deliver, by the way? Okay, 3. So this is called triprotic. H2SO4 is diprotic. But you see, when this delivers the proton, it becomes H2PO4 minus. It delivers another proton. It becomes HPO4 minus 2. Do you see the trend here? It delivers the third and final proton. This is minus 2. It becomes phosphate PO4 minus 3. So here's the first proton that comes off. Here's the second proton that comes off to give you HPO4 minus 2. And here's the third proton that comes off to give you phosphate. Okay, you may have heard of phosphate if you're in biology class. So what I want to tell you is that, you see, this first proton is very acidic. Okay, so it comes off easy. All right. This second proton, we'll call this proton 1, proton 2, proton 3. The second proton in this triprotic acid, known as phosphoric acid, not as acidic, okay, in terms of giving away, okay, giving away. Who wants to give away the protons? H3PO4 can give away the protons better than H2PO4 minus. What about HPO4? This giving away a proton is very poorly acidic. Okay. What am I trying to say in all of this? What I'm trying to say is that the first proton is very acidic, but the second proton, the third proton, okay, it's not so acidic. So the first proton comes off easy. If I was phosphoric acid, I can give away my first proton, my second proton, not so much, and then my third proton, not as much at all. Okay, so the first proton comes off easy. It's very acidic. The second and third, not so acidic. The diprotic sulfuric acid, the first proton comes off pretty good. It's very acidic. That second proton to give you HSO4 minus. Will this second proton come off as easy? Not so much. Okay, so that's the take-home point. So hopefully this becomes clear with some numbers. Okay, so here is H3PO4. Okay, this is the first proton that comes off. The first proton that comes off, giving us H2PO4 minus. And that has a Ka of 7.5 times 10 to the minus 3. Pretty weak. Let's look at our second proton. Because remember, this guy can give us a second proton. And when it does, it gives us HPO4 minus 2. This does not come off as well, right? 10 to the minus 4 compared to 10 to the minus 3. Just look at the numbers with me. And then finally, let's highlight this in green. How good does HPO4 minus 2 give away its protons to give you phosphate? Okay. This HPO4 minus 2 to give off its proton to give you phosphate has a Ka of 10 to the minus 13. 10 to the minus 13. Think of that. 10 to the minus 13 is a very, very small number. Okay, so the first proton comes off pretty well in phosphoric acid, 10 to the minus 3 Ka. The second proton does not come off as well, 10 to the minus 4 Ka, And then that last third proton, this last equation, that third proton does not come off. If it does, it's very, very, very weak, 10 to the minus 13. Okay, so first proton comes off pretty well, second proton not so well, third proton very, very, very poor acidic quality. All right? And remember, as your Ka goes up, your pKa goes down. Okay, that's the trend. Or as your Ka goes down, your pKa goes up. Okay, that's the trend. So, yeah. Let me just add one more thing here. This was in my notes. Okay, here. Subsequent protons becomes weaker and weaker. That's the trend for polyprotic acids. The first proton comes off pretty well. Second, third protons, not so well, based on their Ka, or you can use the pKa. All right, so this one is a problem that you can look at online. So if you do have the time, you can watch this video and do the problem with me. If you don't have time, that's okay. You don't have to do it. But if you know how to do this problem, really all the other problems just become very easy. Okay, this is a polyprotic acid, oxalic acid, and you got to do your ice table twice. Okay, one for this equation, and then the other one for this equation. So check out the video if you have time. This will really hone in and sharpen your skills with these ice tables, as well as working with polyprotic acids. This is called oxalic acid, and it has 2 protons. So watch the video if you have time, and it will definitely very good practice. All right, finally, in this page, we want to talk about how strong an acid is. Okay, so here, remember, if we have an acid that, okay, I'll call this an acid. If the A is some electronegative atom, so by that I mean, as an example, the oxygen atom is very electronegative. Fluorine atom is another one. Maybe we can include nitrogen. So what do I mean by electronegative? Okay, it's like a vacuum cleaner. The pulling power, the sucking power of that bond. So if it's an oxygen, fluorine, or nitrogen, it's pulls. See, this is not a fair 50-50 even bond. The oxygen, definitely the fluorine, which is the most electronegative element in the periodic table, it pulls. Okay, it pulls. And when you have something that pulls and pulls and tugs in a tug of war, it's pulling, this H can easily come off. Okay, can more easily come off, because remember, acids deliver protons. But if you have something that's pulling at this bond, pulling, okay, it's going to pull that electron to itself and liberate H+. So pulling power of the electronegativity makes it more acidic. Okay, HA is just any old acid. So as an example here, let's go to our final page of the notes. The question for you guys is, which of the following acids is weaker, HClO2 or HClO3? Okay. Bless you. All right, so how many oxygen atoms are here? 2. How many oxygen atoms are here? 3. What does oxygen do? Which has more pulling power? Molecule that is 3 oxygens or 2 oxygens? More pull? 3. Okay, so because this has 3 oxygens, we expect this to be the stronger acid. Okay. Bless you. Why? It's pulling, and if you're pulling, you're pulling, you get those electrons to yourself. Okay, there goes that H+, which is what acids do. They liberate and give off H+. So this would be the stronger acid. Again, an acid in this sense means delivering H+, and this would be a weaker acid relative to HClO3. Okay, remember, the more electronegative atoms, the more muscle, the more pull. It's like a tug of war. Okay, if we have 3 people versus 1, okay, the 3 people are going to pull on the rope, leaving the other guy behind. Okay, here the 3 oxygens as well as the Cl are going to pull on those bonds, leaving the H+ behind, leaving the acid behind, making this the stronger acid. So oxides and just really quick here. Oxides and hydroxides can also be acids or bases. So going over these reactions with you. Sodium oxide, if you remember, oxide is this. Okay. So here you have sodium oxide in water actually being a source of a base. Sodium oxide is a source of OH minus. Okay, CO2 gas is a source of an acid. Diprotic acid, that's called carbonic acid. This reaction actually happens in your body. This is for all the biology majors. This happens very much in the body. It's important for buffering of blood, but it's a source of an acid. Source of H+, CO2 gas. Okay. So you see here we have carbon dioxide, sodium oxide, dinitrogen pentoxide is a source of an acid, nitric acid. Source of H+. So here's some oddball chemicals, some very odd chemicals. Sodium oxide giving rise to a base. CO2 gas, which we exhale, and plants do photosynthesis with it. That CO2 is a source of the acid, and this gas, N2O5, is a source of H+. So some weird chemicals and weird behaviors. I think that's interesting as far as on the exam. Probably not going to test you on it, but I think it's interesting how this oxide, how carbon dioxide gas, which we all are familiar with, and how this gas is a source of an acid and base. Okay, this one being the source of the base, these 2 gases being the source of acids. All right, finally, what we've been talking about are Brunstad acids and bases. Here we have Lewis acids and bases, something that I have not really talked about. But here, a Lewis acid actually, so this involves electrons first and foremost. Okay. So here we're having a Lewis base is something that donates electrons. So a Lewis base is actually kind of like nitrogen with a lone pair. So you always look for a lone pair for a Lewis base. And then a Lewis acid is something that has no lone pairs of electrons. So, not going to test you on this, but in the literature there is Lewis acids and Lewis bases. What we've studied here in this entire chapter was Brunstad acids and bases. Okay, which involve H plus transfer. Proton transfer. Okay, somebody takes a proton, somebody gives off a proton, the bases take the proton, the acids give off the proton. Brunstad acids and bases. Okay, in your study, definitely in not organic but inorganic chemistry, you'll talk about Lewis acids and bases. All right, so that will wrap this chapter up. I'll see you all in lab. If not in lab, I'll see you on Monday. So have a good day.